Alright, today we're going to take a look at how to derive our thermodynamic factor matrix in equation 1-32 from our driving force for diffusion of non-ideal fluids from equation 1-30. So kind of to start off, taking a look at our first equation here, 1-30. So again, this is our driving force expression for diffusion of non-ideal fluids. This is in terms of our chemical potential gradient. When we're looking at that chemical potential gradient, these symbols here are just essentially showing that this can be expressed in terms of anything from partial pressures to mole fractions. Today we're going to take a look at this in terms of mole fractions. So kind of to start off, what we're going to do is we're first going to rewrite this expression in terms of mu. So I've taken our mu from our chemical potential gradient here, and I've just put it into our derivative expression here. So what we're going to do next is, so this mu is actually derived itself from expression from Gibbs free energy. So that expression is mu I is equal to mu I at our standard condition plus RT natural log of gamma I xi, where this gamma is our activity coefficient for that component and our xi is our mole fraction for that component. So what we can do is we can go ahead and substitute this expression into our driving force equation. So we'll rewrite that as di equals xi over RT, and then we'll just write this as dz standard plus RT natural log of gamma I xi. So next step we're going to do is we're going to go ahead and actually take the derivative of this part of our expression here. So when we do that, we'll go ahead and rewrite, well, actually starting off. So when we take the derivative of this is essentially going to be 0, because that's our constant by itself. So we'll go ahead and rewrite our di is equal to xi over RT. And what we'll do is we'll actually go ahead and we'll pull out this RT because that's going to remain constant through this as well. So we'll go ahead and we'll pull that out front here. So that'll give us dz of our natural log of gamma I xi. We'll go ahead and cancel out these RTs, and that'll leave us with di is equal to xi, our mole fraction of component I, times the derivative of the natural log of gamma I xi. So we'll go ahead and we'll take the derivative with respect to the natural log first. So that'll give us di again equals xi times 1 over gamma I xi, leaving us still with the derivative of gamma I xi. So from here, what we can do then is you can see we have our mole fraction of component I in both the numerator and the denominator here, so we can go ahead and cancel those out. So then di is going to be equal to 1 over gamma I times dz of gamma I xi. So from here, we'll go ahead and we'll do the chain rule on this element here. So what we'll end up doing is we will do di equal to 1 over gamma I. Gamma I with respect to mole fraction of component I plus mole fraction of component I with respect to gamma I. So once we have this expression here, we can go ahead and actually distribute our constant out in front into what we have here in the parentheses. So what will end up happening is that these two components will cancel out with each other, leaving us with our expression di is equal to dxi over dz plus mole fraction of component I over gamma I times gamma I over dz. Now when you look at this expression here, this can actually get simplified even a little bit further. So when you see that this is essentially here, what this is essentially is 1 over gamma I, or the derivative of gamma I. When you look at it in respect to this, this is essentially the natural log gamma I. We're essentially going to take what would be like the integral of what this is, since it's in terms of itself. So this is essentially our derivative of our natural log of gamma I, or if it's easier to read it this way, yes, the derivative of our natural log of gamma I. So we'll go ahead and we'll take this expression here and we'll plug this back into what we have here. So that's going to leave us with driving force is equal to dxi dz plus xi times the derivative natural log gamma I with respect to z. Now, since we're dealing with a multi-component we're essentially going to break this down to compare each individual component to the other components of the mixture. So in order to do that, what we're going to kind of do is we're going to express this term here in terms of the partial derivative for each component in our mixture. So what that'll kind of look like is our di is going to be equal to dxi or dz plus xi times, in a whole, the partial derivative of gamma I, natural log of gamma I over whichever component we're looking at. So for example, if we look at a 3-component mixture, we are going to show this expression in terms of each individual component. Now, it doesn't have to necessarily be a 3-component mixture. It could be less than that, it could be more than that. It just depends on the situation. So what this will look like if we have a 3-component mixture is, so if we look at the driving force for component 1, that's going to be dx1 over dz plus x1 times the partial derivative of natural log gamma 1 over x1 d x1 dz plus partial derivative gamma 1 So essentially what we're doing is we're comparing the activity coefficient for component 1 with respect to each other component in the mixture. So this essentially would just get repeated for component 2 and component 3 as well, which I'll try to quickly write out. Okay, so now that we have each component written out in terms of our driving force expression here, what you can kind of see is this is already starting to look kind of in a matrix form, and that's what we'll end up doing here in a second. Just one thing to note is that, so all of these driving forces for each component, that's essentially equal to the total driving force, again, that we were expressing here. We just write it in terms of each component individually, comparing it to the other components in the mixture. So This is essentially our like I said before, this is essentially our matrix here. What I'm going to go ahead and do is actually rewrite this in matrix form. So I'll put this back up here. So essentially what's going to happen is our first 1/3 vector is going to be the driving force for each individual component is equal to our natural log of our activity coefficient for component 1 with respect to the mole fraction of component 1, and then the activity coefficient in respect to mole fraction of component 2, and then component 3, and so on and so forth. So we'll go ahead and write what that's going to end up looking like. So this here is showing so far each component compared to the other components. So for here we've got our activity coefficient and our mole fraction of component 1 compared to the mole fraction of component 1. Here we've got the activity coefficient and the mole fraction of component 1 compared to the mole fraction of component 2. And here we've got the mole fraction and activity coefficient of component 1 compared to the mole fraction of component 3. So on and so forth, it goes down the rows. And what we have that multiply by is another 1/3 vector, and that is the derivative with respect to each component. So we've got dx1 over dz, dx2 over dz, and dx3 over dz. And see how these derivative expressions are aligned with the driving force for each component that we're looking at. So mole fraction of component 1, the driving force of component 1, and 2, and 3, and it continues so on and so forth. Essentially what we're looking at here with this matrix is actually, so again, the summation of each individual component's driving force is equal to di. So then overall our di from this expression can be seen as the summation of our thermodynamic factor matrix from j equals 1 to n times our mole fraction gradient, which is what this 1/3 vector represents. Well, that's that. That's the mole fraction gradient of xi. So this is essentially our equation 1-31, which we hit along the way, working up to 1-32. So since we know already kind of what the mole fraction gradient is, that's essentially just dxi over dz, which can be found here. What we need to do is specify what our thermodynamic factor matrix is equal to. because that essentially, if you remember from right at the beginning, that is what we're looking for here in 1-32. We're looking for what this value is equal to. So again, since this whole matrix here is considered our thermodynamic factor matrix, so that is, we're going to break down what this is. So right off the bat, from looking at kind of each component, we can already tell that it's going to be at least partial derivative of the natural log of that component, its activity coefficient, so gamma I, over partial derivative of x j, which, so this I in this case is depicting which component we're specifically looking at, like the driving force of, and then the xj here is what we're comparing it to. So again, kind of looking back on here, in like the first row here, we're looking at the mole fraction, the driving force of component 1. So we include the mole fraction and activity coefficient of component 1 with respect to component 1. And then as we move down the line, you'll see for the driving force of component 1, we're looking at the mole fraction of component 1 and the activity coefficient component 1 compared to the mole fraction of component 2, so on and so forth, component 3, and then it does the same. We do the same thing for each row. So we know that this is one part of our expression here, and we'll multiply that by x of whichever component we're looking at. So again, that'd be xi for us. Okay, sorry about that. So what I was getting at, the last part we were looking at is, so again, the last part we added was the mole fraction of component I, which is in respect to the driving force of the specific component we are looking at. The last part that you may have noticed here is that some of these falling in this diagonal pattern here include a 1, an additional 1 to them. So what this is called the Kronecker delta, and that's represented by this delta symbol here. So essentially what that says is if I is equal to j, then the Kronecker delta is equal to 1. And if our I is not equal to j, then our Kronecker delta is equal to 0. So that's why in this case we have an additional 1 here, because our I, which is 1, is equal to our j value, which is also 1 for component 1. Whereas when we go down the line diagonally here, we don't get that additional 1 until we hit the I of 2 and the j of 2 and then the I of 3 and the j of 3. For all the other instances where I does not equal j, that would be 0, and we can include or not include the 0 because it doesn't matter. It might be easier to understand if we include it, so that's essentially just saying 0 plus the rest of our expression here. So that's the last part here. And ultimately that is what our thermodynamic factor matrix is. And then I rewrote that here just for an easier visual. So yeah, that's how we get from equation 1-30 to our equation 1-32, our thermodynamic factor matrix.